So let's do some examples with Lewis dot structures that contain elements, that contain atoms that are exceptions to the octet rule. We'll do this center one, PCl5 in class, but let's focus on BEH2 and XEF2. So let's go ahead and do the Lewis dot structures for those two, using the rules that we talked about in the previous video. So first things first, number of valence electrons. So for BEH2, hydrogen in group 1, there's 2 of them. Beryllium, group 2, have a total of 4 valence electrons. Get my little pointer here. Now let's go ahead and do the Lewis dot structure for BEH2. Looking at my electronegativity, I see that beryllium, and remembering that hydrogen is always terminal, beryllium has got to be in the center. I'm going to scatter my 2 hydrogens around it. So I have made my skeletal structure. I'm now going to distribute my 4 valence electrons by first doing single bonds. 2, 4. I've used all 4. My hydrogens are happy with a duet. Beryllium does not have an octet, but remember it is one of the exceptions that can have a less than an octet of electrons. So this is the correct Lewis dot structure for BEH2. Now let's do something with an expanded valence, XEF2. We're going to start by doing number of valence electrons. I can draw this, number of valence electrons. Xenon, noble gas group 8. I've got 2 fluorines, each in group 7, so I've got a total of 22 valence electrons. That xenon is going to be my central atom. It is certainly less electronegative than the fluorine. Scatter my fluorines around it. Start making my single bonds. 2, 4. Complete the octets on the outer atoms. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I've now used 16 of my 22 valence electrons. We said that any extra valence electrons after completing octets on the outer atoms, any extra electrons go on the central atom. 17, 18, 19, 20, 21, 22. So xenon certainly has an expanded valence, more than 8 valence electrons around it, but that's one of the exceptions. So that is the correct Lewis dot structure for XEF2. And we were able to deduce those properly by using the rules from the previous video. Now let's talk a little bit about Lewis dot structure trends with regards to bond properties. So this concept, we'll revisit it later, of bond order. When we talk about the bonds in a molecule, we can describe that bond with regards to polarity, but we can also describe it with regards to its length and its strength, and both of those are reflected in this quantity called bond order. Bond order in this example is essentially going to be number of bonds. So if I was to look at 3 different carbon molecules, one with a single, one with a double, one with a triple bond, I see that as my bond order or my number of bonds increase, the length of that bond decreases and also the strength increases. The strength that it takes to break that bond apart. So that means it is more stable. That is a trend that you need to know. You should also know that when comparing bond lengths and energies with hydrogen and different halogens, as your halogen size gets larger, the distance of that bond increases, and therefore the bond strength decreases. So you should know the trend with regards to bond order and with regards to bond length and bond strength.